Today we're going to do this problem to illustrate how we can find the distance between two parallel planes. Now we have two equations for the two planes. X plus 3y minus 5z equals 7 and x plus 3y minus 5z equals 10. They're obviously parallel because their coefficients 1, 3, negative 5 and 1, 3, negative 5 are multiples of each other. And this means that their normal vector is in the same direction. Therefore, these equations, the planes of these equations are parallel. I've drawn these two planes. I know the distance between them. So basically, this line that is perpendicular to both planes. Okay, so how do we do this? Remember when we tried to find the distance between a point and the plane? All we did was we used projection because, so we essentially just found a vector. So we found a vector on this plane. And what we did is this. We found a random point on this plane. We connected that point to the original point we want the distance of. And then what we got was, and then the distance is actually just the projection of this new vector. The distance is actually just the projection of this new vector onto this normal vector here. Because this is actually, well, it's actually part of the normal vector, right? That's actually the normal vector. So it's basically the projection of the blue vector onto the green normal vector. So how do we know what the blue vector is then? We know the normal vector because from the coefficients we can figure out that the normal vector, so the normal vector, vector n, is equal to 1, 3, negative 5. Right, that's our normal vector because that's from the coefficients of, well, these equations. Now what about the blue vector? The blue vector, let's just call that vector A. Vector A is equal to, well, first you want a random point on this plane. Let's just say that this is here. That's this plane. This plane here is x plus 3y minus 5z equals 7. Well, the first point you can think of should be 7, 0, 0. Because if you just plug 7 in, right, then you plug 0, 0, you actually get 7. Well, we're using the same logic. Another point to think of is, well, so another point to think of here is going to be 10, 0, 0. So that's 10, 0, 0. Okay, so we want the projection of, well, 7, 0, 0 onto this vector. So we want the projection of vector A, which is going to be 3, 0, 0 onto the green vector, the normal vector. Now we know how to do this because, well, firstly, we only want the distance, so we're going to use comp. We're going to use comp, C-O-M-P, and then vector A onto vector N. This gives us the distance, and this is equal to, this is equal to, well, the distance of the magnitude of vector P, which is this vector here. And then so what is it equal to then? Well, it's also equal to the absolute value of the dot product of vector A and vector N over the dot product of N. Over the magnitude of N. Why do we have an absolute value here? Because essentially we want positive values for the distance. This may be negative, so we want positive values for the distance. Okay, so if we evaluate this, this is going to be equal to the dot product is going to be 3 plus, the dot product is going to be 3 plus 0 plus 0. The dot product is 3. The magnitude of vector n is going to be root 1 squared plus 3 squared plus 5 squared. 1 plus 9 plus 25. That's equal to 3 over root 35. That's 5 times 7, so we can't really evaluate that. Well, we can simplify this. So we have 3 roots 35 over 35. So this is our answer. So in general, what you have to do is find 2 points that are on each plane. So 1 point here, 1 point there. Then you find the projection of this vector connected by the 2 points onto the normal vector. So thanks for watching. Bye.